So code has been generating ambiguity-fixed block products since mid of this year. So I will introduce the new features of these block products, and I also would like to emphasize the importance to carefully consider both clock parameters and bias parameters at the same time. This is the outline of my talk. So the new clock products, then some widelane bias results, how the clock generation works, how we represent the phase biases. Then an important part is to show the properties of the new clock and bias products on the basis of a series of plots, validation parts, summary and conclusions. And here you have an overview over the three analysis lines where we have ambiguity fixed for the clocks. So rapid, final, and the multi-GNSS. Then you have indicated here the systems included in red. There we do narrow-lane ambiguity resolution, so wide-lane we do for every system. Then the temporal resolution for the clocks, the elevation mass angle, the number of stations typically included, and the starting GPS week where we started to provide the product. Important, by the way, is also a feature we added recently, is we added the 24 UT epoch to the final clock product. This is just done internally, not yet provided to the IGS, but this allows them to compare at one specific epoch the product from the previous day to the next day. This is a comparison of the widelane, GPS widelane fractional biases compared our final product with those provided by the French colleagues from the GOG CNES group. So this is on a level, oh, this was already. So this is shown here, this is at the level of 100th of a cycle. So excellent agreement, this seems to be a straightforward task. And when we compare our values, so between consecutive days, then we're even on a lower level, so on 0.005 cycles. When we compare that with different lags, so the values you obtain now with those you obtained 30 days ago, they look like this, indicating that GPS values tend to slowly vary in time. This is the situation for Galileo fractional biases, previous day to current day. And the interesting thing is when you do that for different lags, this indicates that the Galileo values are pretty much more stable. And when you have a close look at this, that you could see that the bright blue and dark blue curves tend to be even below the 1 day lag curve. And this might be attributed to the fact that Galileo ground track repetition period is 10 days. This is how the procedure works. So in blue you have the previous procedure, so ambiguity float, satellite clock estimation, and the new part is shown here in red. So you have first here the ambiguity float clock estimation, then you go once here again back. You have the ambiguities fixed, introduce them, and that's it. This new part includes in particular 4 steps: widelane phase bias determination, integer fixing, narrowlane bias determination, and narrowlane integer fixing, with the main result observable specific bias values, or in our case L1 and L2. In brackets you see the acronyms we typically use to label the products. And with this slide I would like to show how the representation works. So at the beginning, in the GPS case, so we had just one pair of observables. It was obvious that then the clock refers to these observable types. then receivers became available providing other pairs. So you see here then C1W minus C1C TCB was necessary to either correct the observation to make it consistent to the reference observable, or to called here to derive a redefined clock value. And now in red you see the phase observables. For the Narrowlane you have here various candidates, and in our case we have here a Narrowlane fractional bias here, and you see we have one clock. The biases we could refer using the clock information, the bias information, then the information to each observable time. So that's why we call our approach common clock observable specific bias approach. And for comparison, we also included the phase clocks, Chiricari clocks approach. So this then looks like this, and you have a clock then being consistent for phase. What happened with the pseudo-range application is then, at least to me, questionable. Let's compare now the final with the rapid product. So we're in a comfortable situation that we have 3 analysis lanes where we do that in a completely independent way, even with different strategies. By the way, we obtain similar results also for the comparison with AMJAX, but we'll restrict here to the comparison final minus rapid. Now we will get a series of plots. Always we have a scale here with 1 nanosecond. This is 30 centimeters, and here +1 minus 1 Narrowlane cycle. Here you see the units in time and in meters. Color indicated for each satellite. Important here in the following is the observable type. Then here you see a flag for whether the radial orbit correction has been applied and the bias level correction. So for this situation we have a standard deviation of 35 picoseconds. Then applying the radial correction, you see more or less straight lines, this level for the pseudo-range clocks. And then when you apply the phase corrections, we get these kind of lines. The standard deviation is then of the order of 100 up to 200 picoseconds. We will see that later then in the IGS ACC plots. And because the widelane ambiguity-fixed is completely different in the final and rapid product, the biases are needed to reconstruct or to make the information consistent to each other. This is done here, and you now see 3 sets of lines. This is, by the way, an unhealthy satellite. There we typically see, due to the lack of data, the rapid and AMJAX analysis problems. So this is also very helpful to indicate issues in the data. And finally, you can reduce here the Narrowlane cycle, and you end up with an agreement for this particular day at the level of 7 picoseconds. Now let's continue with the comparison at the day boundaries. So here, pseudo-range solution, and then phase. And because we are already internally following the same similar procedure in the final, already without applying any correction with the standard phase biases, we end up here with this plus minus 1 Narrowlane cycle results. Can correct this, and again we are at the level well below 10 picoseconds agreement. So this indicates that we can connect, we're able to connect the clock products between 2 consecutive days. This is, by the way, the radial correction turned off and again turned on. So because we use a middle day of a 3-day analysis, this correction is pretty small. Now the validation part, we did a lot of studies. I just restrict here to 3 possible validation. So this is the outcome from the PPP analysis. In blue, ambiguity float. In red, ambiguity fixed. Statistics created for September this year. And you reduced here the number of stations that really just stations were included where we had a significant number of days contributed. And what you see here are roughly a factor of 2 for the east component as expected. As another validation is shown on a poster created by one of my colleagues, Daniel Arnold. Here we generated the integer clocks for April 2007, also confirming that our strategy works for older data, and he could validate that with race K-band data, and could show that without further fine-tuning, the zero difference application is already pretty close to the double difference based on baseline. Also, we referred to this poster. And this graph we already saw in Michael's talk. So this is the cheapest week where we started. And interesting is that first we can say that an AC starting with ambiguity fixing may expect roughly a factor of 2 in this particular matrix. And so this means code, ESA, JPL, GFZ. I guess they provide ambiguity fixing. And then here the EMR group, Wuhan, I would say they still go with an ambiguity float solution. And what you also see here is the level, so well below 10 picoseconds. This is for the rapid. This is for the final. Here we have now the French colleagues here from CNES. And what we also consider important is the other metrics where we do not reduce bias mounted to satellite clock. So this is then relevant for those applications where users rely on pseudo-range, supported to pseudo-range only applications. You see that code is on a pretty nice level, so you could serve both applications, phase and pseudo-range applications. And here, again, you see the values. So upper between 100 and 200, indicating that these clocks here are precise for PPP, but they are phase clocks. In summary, code has established the generation of a high-quality signal-specific bias product and a fully consistent ambiguity-fixed clock product within its rapid and fine IGS-related processing. And our multi-GNSS clock product contribution to AmChecks does include ambiguity fixing not only for GPUs but also for Galileo. All presented developments are part of the current development version of the bonus software. This quantum leap in GNSS clock analysis could be accomplished due to successful between satellite ambiguity fixing using high-difference observation data of the IGS network. The new code clock products reveal a notably improved quality and in the end allow for single receiver ambiguity resolution, thus enabling integer PPP. Our new clock and bias products are conditioned in a way that maximum consistency may be ensured for first ambiguity float, secondly ambiguity fixed, but also for pseudo-range support or in the extreme case, pseudo-range only PPP applications. And in any case, the clock product has to be used in conjunction with the associated phase and pseudo-range bias product in order to achieve best possible performance. And again, this 24-hour UT-book we do not yet provide for the IGS, permits us to connect the fan clock product between consecutive days to create longer, consistent clock and bias information for longer periods. And this is the only equation I have. So this once more underlies that with biases and clocks you can very easily compute redefined clocks with respect to a new observable set with the reference clock minus the ionosphere field acceleration, OCD correction for here. And this means for the user, with our approach, you have in blue the pseudo-range corrections and in red the phase corrections, so he just has to decide which observable is involved, independent whether he is using the Melbourne-Wuhan linear combination or the ionosphere linear combination. That's all from my side. Bye.
Thank you, Stefan. I'm sorry we don't have any time for questions right now. We'll have to go straight to the next talk, which is from Felix.